In a previous video, we demonstrated that you can actually get meshes from the depth information. And so meshes are very useful, and there's a bunch of uses that we can do with them. And today I wanted to focus on doing physics with those meshes. So we're going to be capturing information from the camera, turning that into a mesh with motion, and then using that mesh, we are going to introduce some physics to it. So we will be doing collisions today. So we are going to be looking at what happens when objects are thrown into that mesh and seeing how it looks, and then eventually we're just going to make the mesh transparent and we'll see how it looks and whether it actually looks like we're colliding with real world objects or not. And that's going to be the focus of today. So we're using a really old physics engine known as the bullet physics engine, and it's really good at dealing with geometries that are very simple, but it does have some difficulties with more complicated geometries. It's not the optimal for colliding meshes, and so that's something that you can notice by looking at the footage very easily. You can see that there are collisions that happen where the collision keeps happening afterwards, so there's a lot of jittering of resting objects, which is not ideal in a physics simulation and isn't what we want to see. So we might test out a few other physics engines as well in the future, but for now this shows what's possible with physics engines and augmented reality. The thing that kind of popped out is that the depth maps are not quite good enough to give you a super strong sense of immersion, but they are also strong enough that you can get a sense of what's happening. So you can get a sense that these objects are lying on top of things or that they are colliding with things. So it's kind of on the verge of, we're kind of in the uncanny valley right now. We're not quite at the point where it's believable, but you can start to see that something is happening. So it's a really good proof of concept, but it's not great at actually showing the value of physics engines and AR quite yet. But I think it's exciting because it's like, we're getting there. And also this is on, once you have some more advanced technologies like LiDAR and common phones, then I think it makes everything a lot more straightforward. So I also wanted to mention that you can actually combine different meshes together by taking multiple meshes. But one of the issues that does come up is that it's kind of an additive process and not a subtractive process. So you can end up having extra walls in your scene if you take multiple meshes. That's something that you'd have to do some remeshing or some extra work in order to do any sort of mesh subtraction. So it's just additive. So one thing to recognize is that there's a huge amount of throughput that has to get through the system with the depth image. So I don't know if actually having a higher resolution of depth image would automatically make this more responsive. It would likely just clog up the system. So that is kind of something that, even though we aren't using the highest resolution depth image, is probably an issue with using LiDAR or some other method. So if you had a really high LiDAR mesh, it would be a little bit more complicated to do all the physics on a cell phone in real time while keeping track of all the other variables that you need for AR. Because one thing that is also a little bit interesting about AR versus some other system is that if you lose frame rate on AR, it becomes really disorienting because you actually can't do the computations for the position integration. So whereas other systems, it will just have some sort of stuttering, a lot of times in AR, you'll end up with a drift away from the image, and that can actually lose your sense of immersion. So frame rate is incredibly important in AR, and ensuring that you have a certain stability to that is very important. The Bullet Physics engine is a really good tool to use with Three.js because they have a lot of overlap in their syntax and how they operate. So it's really easy to get values from your 3D image into the physics engine and then back. So quite a lot of the resources from this particular video came from Simon Dev. So they are someone that does Three.js videos without any sort of AR. And so a lot of the stuff with the physics collisions came from there in Three.js. I just ported that into augmented reality with the depth mesh that we had previously been working on. So it's really helpful if you just kind of start combining ideas from different people together in AR or in VR. You can get some really interesting results just by working with other people's ideas and kind of mishing and mashing different people's ideas together. So we're just going to start with the depth mesh project that we had previously been working on. And so if you're having any sort of confusions, maybe just go back and look at that video and then come back here if you did have any sort of confusion. So to start off with, we're just going to initialize some sort of worker. And this is going to be where all of our physics is done. So our physics engine is going to be off our main thread, and we're just going to communicate it through messages. So for every time that there's an update from our physics engine, we will get a message. And then anytime we need to add something to the physics physics engine, we will message it. So the update function is going to be a pretty heavy function that does a lot of the work for us. So it has to update all the positions and orientations of all of the meshes. So we are going to put all of our physics objects that are moving around inside of a 3 group known as meshes. And then whenever we get an update, it's just going to update our position and rotation with those values. So the next thing that we have to do is we have to give the physics worker the mesh from depth. So we had this depth mesh that we had previously created. We need to hand that over to the physics API in order for it to actually use that mesh. And we have to give it a few other values too, just for the initialization of that mesh. And so these are just all the variables that we have to give them. Some of these are not necessary actually. I was doing a lot of experimentation, so there's some vestigial code here, some code that's not entirely used that we don't need. So now that we have all of that, we're going to add in some Raycasters. So when we click on the screen, we want to be able to add different physics objects to our scene and to our physics engine. So we are going to create a raycasting function for touches and mouse touches. And so that function will just be called. We need to get the mouse from that object, and we need to add that to our raycaster. And so now our raycaster is casting into our Three.js scene with the vector from the mouse. And we will get the origin, and we also have the ray for the initial velocity that we want to use. So now we're basically just adding in the Three.js objects, and we're going to randomize the color with HLS. I just like this color space a lot more for when you're creating random colors. It makes all the colors seem similar to one another. So I just enjoy that way. So once we have the meshes added to our Three.js scene by adding them to the mesh group, we will post a message that will add it to the physics engine as well. And the only thing that's really unique about this is that the initial velocity that we give it, we want to get from the ray, and we'll just multiply it by a value so that it's large enough that it looks like you're actually throwing something. So the first time I did this, the initial velocity was not high enough and it just looked like it was dropping things. And so now that we've done all the communication with the actual physics engine, all the physics actually just happens in the engine. So we'll look at that code afterward. So ammo.js, there's quite a few examples on, and it has a lot of default configurations that it doesn't do automatically, but you just have to declare. And so these are just kind of, this first section is just all of those declarations of configuration, and we're just not really going to touch any of that. It's pretty necessary. One thing that I will make note of is that there is also a WASM version of ammo.js that's probably faster, but since we're working in a web worker, it was having some issues, so it wasn't working the way I was it just wasn't working. And so that's probably because I'm not sure if WASM is actually available within a web worker, because WASM itself is usually started on new threads, so that might have been the issue. It might actually be faster to run ammo.js WASM on the main thread than create a web worker for ammo.js. So that's something that playing with it in the future, I might try that out. But anyways, simulate is the main function. With this section, there's quite a few things that I just didn't touch that might not do anything because I was having some difficulties. So there's kind of this idea of let line code lie and lane code lie. And there's also this idea, if you want to be more professional, about how you shouldn't remove things before you implement tests. And I didn't implement any tests, so I shouldn't have removed anything. So there's the professional justification. But anyways, so simulating is the main function that's going to be called over and over again. So the main thing that we're going to have to do unique here is we have to send back the information about our physics world on every single simulate. So this will be kind of the messaging function that will get us back. And once we have that, we're just going to have to set up some receiving functions for when the worker receives information from our main thread. So that includes the mesh and the objects that it builds. So the updating is just happening through an array of objects that's just gathering our information from the shapes. And it does that by getting the world transform and then placing that transform inside of the objects. And that will get us back to the main thread. And then there's one thing that we kind of wanted to do is build out a ground floor. And so the ground floor is basically just going to be a really large box that we're just going to put under ourselves that has zero mass. So in ammo.js, when something has zero mass, it doesn't work in the physics engine. So things don't move. It's a good way of setting off your ground is by having zero mass. So the Three.js mesh is a little bit more confusing in how to implement it. So we basically have to add in all of the information that is included in Three.js object into the actual vertices. So that's this loop here, is it's kind of applying all of the information from our matrices into the physics object so that just the physics object has all of that information. And once we have the actual shape, it's pretty straightforward and similar to all of our other methods where we just kind of set the transformation, set the shape, and then build out the object. So most of ammo.js is kind of set up in this 3-step process where first of all, you kind of define the rotation and transform of your object. Then you kind of describe the shape of the object, and then you describe some of the physics characteristics of the object, and then you combine that all together. So there's kind of that 4-part process, and you'll see that for all of our objects. So this is just a giant box that we're going to be creating. Then we're going to create a sphere and a cube. Thank you and have a good day. And I'll just leave you with some different videos showing the different collisions that we worked on today. Have a good day.